In this topic, we're going to look at how to express the equation of a line in vector form in 2 dimensions or 3 dimensions, either using column vectors or the unit vectors I, j and k. A line can be expressed in vector form using this equation. R equals A plus lambda b. R, A and b are all vectors here, and lambda is a scalar. R represents any point on the line. R is shorthand for the vector xy if we're working in 2 dimensions. If we're in 3 dimensions, R is shorthand for the vector xyz. A is the position vector of a point that we know lies on the line. B is the vector that represents the direction that the line is travelling in. And lambda is a scalar which, as the scalar increases or decreases, moves the point along the line. So what is happening here is we are starting at the origin. We are travelling to the line using the position vector, A. We are then using multiples of the direction vector B in order to travel to any point up or down the line. Here's an example in 3 dimensions. We want to find the vector equation of a line that goes through the point 1, 0, minus 4 and is parallel to the vector 2, minus 1, 3. So for this, we can use the vector equation of the line. In this case, R, A and B are all 3-dimensional vectors. A is the position vector of a point on the line, so we are going to use the vector 1, 0, minus 4 for A. B is the direction of the line, which we know is 2, minus 1, 3, as it's parallel to that vector. So any point on that line can be found using the equation R equals 1, 0, minus 4 plus lambda 2, minus 1, 3. This time we want to find the vector equation of a line passing through 2 points. Again, we're going to use the general form for the vector equation of a line, and we can use either of the 2 points, A or B, as the position of a particular point. We're going to use A here, so we're going to use 2, 3, minus 2 as the position vector. To find the direction, we need to find the vector from A to B. So the vector from A to B can be found by doing OB minus OA. We have OB and OA because that's just the position vectors of points A and B. So AB will be the vector 1, minus 5, 1. So the general equation of a point on the line is R equals one of the position vectors, 2, 3, minus 2, plus lambda times the direction, 1, minus 5, 1. Pause the slide now and find the vector equation of each of these 3 lines. In each case, you have 2 points that lie on the line, so you'll be able to use the same method as in the previous example. So the equation of line 1 is given there, the equation of line 2, and the equation of line 3. Notice that different parameters have been used in these questions. Line 1 has used parameter lambda, line 2 has used parameter t, line 3 has used parameter s. It's common to use different parameters with different lines if you're working with different lines in the same question, because the parameters may not have the same value for each line. Vector equations of lines can also be found using unit vectors. In 2 dimensions, they're the unit vectors I and j. If you prefer to use column vectors, you can always convert a question into column vectors and then convert back later on. So we're going to find the vector equation of the line passing through points A and B as given. We're going to use the equation R equals A plus lambda B. So for vector A, we can just use the position vector of point A. So r equals 2i plus j. For vector B, which is the direction, we need to find vector B. We can do that by calculating OB minus OA. So minus 3i plus 3j minus 2i plus j. So this gives us minus 3i plus 3j minus 2i minus j. So minus 5i plus 2j. So that is the direction vector of this line. So we can add that onto our equation. Lambda times minus 5i plus 2j. Alternatively, we could write this in column vector form. 2i plus j is the vector 2, 1. And minus 5i plus 2j is the vector minus 5, 2. Those two are equivalent. Next, we're going to verify that the point minus 1, 18 lies on the line with this vector equation. So as in with the Cartesian case, we need to show that minus 1, 18 satisfies the equation of the line. So remember that r is shorthand for xy in 2 dimensions. So we could rewrite the equation like so. What we're going to do is substitute in x equals minus 1, y equals 18, and see whether we can find a consistent value of lambda that satisfies both of those. So minus 1, 18 equals 3, 2 plus lambda minus 1, 4. So we can first of all read across the top line, the x direction. Minus 1 equals 3, and then it's lambda times minus 1, so minus lambda. And across the bottom row we get 18 equals 2 plus lambda times 4, so 4 lambda. If we get a consistent value of lambda for both of these directions, we can say that the point minus 118 lies on the line. If we don't get a consistent value of lambda, we can conclude that the point does not lie on the line. So for the first equation, we arrive at lambda equals 4. For the second equation, we arrive at 4 lambda equals 16. So lambda is also 4. So we can conclude we've got the same value of lambda in both cases. So statement, therefore, minus 1, 18 lies on the line. We can also show that a point lies on a line in unit vector form, ijk. Again, we can do this by substituting the point in for r. So here we have 3i minus 14j plus 15k. That's r equals minus 2i plus j plus 5k plus, I'm going to multiply out this bracket here, so I get lambda i minus 3 lambda j plus 2 lambda k. Now, just as with the column vector form, where we took the I and j direction separately, we're going to do the same here. We're going to take the coefficients of I first, then j, then k. We're going to try to see whether we get the same value of lambda each time. So taking the I direction only, we get 3 equals minus 2 plus lambda. So that leads us to lambda equals 5. If we consider just the j direction now, we get minus 14 equals 1, 1j, minus 3 lambda for the 3 lambda j. So that gives us 3 lambda equals 15. So lambda is 5. And finally, considering the k direction, we get 15k on the left equals 5k, and then 2 lambda k, so 5 plus 2 lambda. Here we arrive at 2 lambda equals 10. So again, lambda equals 5. So we've got the same consistent value of lambda in all 3 directions. So we can conclude that the point lies on the line. Now complete the following questions in exercise 9A on page 197, questions 1 to 3 and 5 to 8.